First, the question, how to evaluate monomial efficiently. Yeah. So here you can see we work on a special polynomial, monomial. Yeah. The structure is very simple, yeah, but the way we do quite different from the polynomial way. Yeah. All right, so let's look at the question. Given a monomial x to the nth power, so it's a power function. Yeah. How to find an efficient way to calculate its value? Yeah. The reference also, because this is a subtopic related to that polynomial evaluation topic from section 6.5. Yeah. All right. So here, because this topic related to the polynomial evaluation, so first let's look at what do we have so far from the polynomial evaluation. Yeah. When we apply the Horner's rule to evaluate a polynomial, we have this main result. Yeah. For a standard polynomial in this form, yeah, and we do not put any condition on the coefficients. The coefficients are arbitrarily given. Yeah. Arbitrarily given, no special conditions on the coefficients. Then in this situation, the result is this. Yeah, so we are satisfied with the efficiency of this algorithm in general. Yeah, in the general case, general situation. Okay? Yeah, so we're satisfied. Yeah, yeah. Very good. Yeah. The best we can do. Yeah. But the question is, this is for the general case, right? Because sometimes we may have some special polynomials. Yeah, what do you mean special polynomials? The meaning of special polynomials, that is, the coefficients may satisfy some special properties. Yeah. Because here, we do not, in this general result, no special property assumed. Okay? No special property assumed. That means we cannot take advantage of any special property for the polynomial. Yeah. All right. But then, another case we also need to consider. If there are some special properties on these coefficients, can we do better than Horner's rule? Right? Yeah. If we have some special properties, that means we can take advantage of these properties, right? Yeah. The general case, you cannot use any property because you cannot assume any property. So that's the main point here. Yeah. So in this small subtopic, yeah, so we want to consider special polynomials. All right. How about the special cases? Yeah. So we will study a few special cases. Yeah. So the first special case, yeah, monomial, right? Yeah. So here you can see this is a special polynomial, very special. Okay. Yeah. So in a polynomial, all the coefficients except one are zero. Only one is non-zero. All the other coefficients are all zero. That's the monomial case. Yeah. So this question, can we do better? First, we consider the monomial case. Yeah. So let's try it. Now we consider our first special case. Yeah. Regarding the monomial, we did one example before. So here, let me start with that simple example we did before, x to the fourth. Yeah. At that time, we use 2 multiplications. Okay, 2. Yeah. Not 3. Yeah, because if you use the Horner's rule, yeah, its leading coefficient is 1. 1 times a power function, x to the 4th. Yeah. So based on our Horner's rule result, we need 3 multiplications. So you can see there is a better way than the Horner's rule. Yeah. Yeah. So let's recall a little bit how to get this 2 multiplication answer. Yeah. The first multiplication, x times x, we get x squared. Second multiplication, x squared times x squared, we get x fourth. That's all we need. 2 multiplications. Okay? Yeah. Now you can see the reason, because we skip x to the 3rd. We skip that. We don't need to calculate x to the 3rd. That's the reason we can save 1 multiplication. Yeah. So this technique we call the repeated squaring technique. Okay? Yeah. Yeah, but we only repeat the squaring operation once. Yeah. Now we can generalize this idea. Can we do more and more repeated squaring operations? Yeah. So let's consider n is power of 2, 2 to the kth, that structure. In that way, let's look at how many multiplications do we need to find this monomial. Okay. So let me do a chart. Yeah, here. The first column, k numbers, second column, the monomial, x to the nth. Then the third column, we count the number of multiplications. Yeah. All right. So the first column, when k equals 1, x squared, 1 multiplication. Very simple. Yeah. Then second k equals 2, this time x to the 4th. Yeah, because 2 squared. Yeah. 2. N equals 2 squared, that's 4. Yeah. So x to the 4th, by repeated squaring, 2 multiplications. Yeah. So next one, k equals 3, we need to calculate x to the 8th. How many multiplications? Right? Yeah. But here, you need to use the result from the previous one. You already have x to the 4th with 2 multiplications. To get x to the 8th, you just need 1 more multiplications, right? So you only need to do x to the 4th times x to the 4th. Another squaring operation. So repeated second time. Yeah. So you get 3 multiplications and so on. Okay. So then by induction, yeah, because you see the rule, right? Yeah. So based on the rule we observed from the first 3 experiments, when k takes the general value k here, yeah, x to the 2 to the kth, that power monomial, yeah, how many multiplications? You do squaring operation k times. Yeah. So you need the k multiplications. Yeah. So that is the result of this repeated squaring. How well we can do by this technique. Yeah. To give you some concrete impression for this method, let me try a concrete number here. Yeah. So when k k equals 10. So let's compare when we use repeated squaring technique and when we use Horner's rule. We want to compare how big is the difference. Yeah. So based on the new result we just derived here, because 2 to the 10th equals this number, 1024. 2 to the 10th. Okay, yeah. Then, remember, the number of multiplications equals k. K equals 10, so the answer is 10 multiplications. If we apply the repeated squaring technique, we only need 10 multiplications. Now, let's go back to look at the Horner's rule. If I ask you to apply the Horner's rule to calculate this monomial, how many multiplications do you need? Yeah. See? Yeah. N minus 1, right? Yeah. Because the degree of this monomial is n. And its leading coefficient is 1. Remember, when the leading coefficient is 1, we can save 1 multiplication from the Horner's rule. Horner's rule, okay? Only we can save 1. So n minus 1. So then the number of multiplication by Horner's rule. Yeah, so here I need to, write the Horner's rule. Answer 1023. Okay, 23. Now you compare 10 versus 1023. How much is the difference? Pretty big, right? Yeah, 1023. Yeah. The major part, if you take out the major part of 1000, the minor part, 23, still more than twice than this, much better result, 10 multiplications. Yeah. So that remainder, 23, still more than twice as the, number of multiplications from the repeated squaring technique. So you can see the difference is so big. So that means when you have the special polynomials, you should try to take advantage of the structure of your coefficients. Okay? Yes. So that tells us, the general case, the special case, when you determine if you want to apply Horner's rule or not. So you need to think a little bit. Okay? So if you have a chance to take advantage of the structure, then you should, do something different than the Horner's rule. Yeah. Only when you cannot take advantage of any structure information, then you have the Horner's rule to give you, the best answer you can get, right? Yeah. So the essence of this method, reuse the resource as much as we can to save operations. Yeah. So this point is very important in our algorithm class. Reuse the resource. Reuse the resource. This point, this thinking is very important in our algorithms class. Yeah. Yeah. So at this point, that's how much I covered in Thursday's class. Yeah. So the remaining